Hello, my name is Tsouros and our paper is on learning Max-CSPs via active constraint acquisition. Constraint programming is considered as one of the foremost paradigms for solving combinatorial problems. A major bottleneck in the use of constraint programming is modeling. Expressing a combinatorial problem as a constraint network requires considerable expertise in the field. As a result, one of the major challenges in constraint programming research is to automate the modeling process, to efficiently obtain a good model of a real problem without relying on expert human modelers. Constraint acquisition is a research area in this direction, aiming at assisting non-expert users in modeling a constraint problem automatically. In this work, we try to overcome one more limitation of constraint acquisition, making one more step in the direction of making constraint acquisition a useful tool for real applications. Constraint acquisition can be divided in two main types, passive and active acquisition. In passive acquisition, the user gives some examples of solutions and non-solutions of the problem that she wants to model to the acquisition system. Then the system extracts a model of the problem that could be derived through these examples of solutions and non-solutions. In contrast, active or interactive acquisition interacts with the user during the acquisition process, posting queries which the user has to answer. The system then extracts the model of the problem when it has converged to its constraint network. Although constraint acquisition has progressed a lot lately, there are still several challenges to overcome. One of the most important ones is that although soft constraints are a very important part of constraint programming, modeling user preferences, constraint acquisition systems have focused on learning mainly hard constraints. There is no study on learning soft constraints via active constraint acquisition. In addition, soft constraints cannot be learned by using the current types of queries that are exploited in interactive constraint acquisition systems. In this work, we deal with this issue, presenting a novel constraint acquisition algorithm that is able to learn the soft constraints of Max-CSPs. In the rest of the presentation, I will first give some background in constraint acquisition and in the related work on learning soft constraints. I will then focus on our contribution. I will first present the new type of queries that we introduced in the context of constraint acquisition, and then I will describe our proposed algorithm that learns soft constraints of Max-CSPs, namely prefACK. Finally, I will give some early experimental results, followed by some conclusions. Learning soft constraints within constraint optimization frameworks such as Max-CSP have been considered as part of the wider literature on learning preferences. There are works proposing systems that infer constraint preferences from given solution ratings or estimating a scoring function via some interaction with the user. Also, weighted first-order logical theories that represent constraint optimization problems are learned in another work. Comparison queries are used in some cases in order to learn preferences that usually are modeled by individual variables. More closely related to constraint acquisition, some works have proposed a learning framework where a constraint network is acquired using a training set of solutions and non-solutions. However, there is no work on learning soft constraints via active constraint acquisition. Let's now see some basics of interactive constraint acquisition. Active constraint acquisition systems use the version space paradigm of machine learning to learn the target constraint network of the problem that the user has in mind. More specifically, they use the candidate elimination paradigm. In this process, we have the vocabulary defining the set of variables and their domains, and is a common knowledge between the learner and the user. We have the language that states the candidate relations that may exist in the problem and is given to the learner by the user. We also have the bias that represents the version space by storing the candidate constraints of the problem, extending the language to the vocabulary. We also have the target network of the problem that the user has in mind but cannot formulate, and the learned network that in the end we aim to be equivalent to the target network. When acquiring hard constraints, the main type of queries that is used is the partial membership queries. These queries ask the user to classify an example as a solution or non-solution of the problem. We can see here an example in a small Sudoku problem to better understand the terms with the variables, the domains, and an example of membership queries. In this work, we present a novel constraint acquisition algorithm that is able to learn the soft constraints of Max-CSPs. In more details, our contributions were the following. We introduce a new type of queries in the context of constraint acquisition, namely partial preference queries, in order to be able to learn soft constraints, as membership queries cannot be used in this process. That is because a soft constraint can be violated both in a solution or a non-solution of the problem. Next, we describe a novel algorithm that, driven by the user's answers to preference queries, can learn the soft constraints of Max-CSPs. We highlight the differences when learning soft constraints than with normal constraint acquisition of hard constraints, and we give some early results that seem promising. Let's now focus on the partial preference queries that we introduce in constraint acquisition. They are inspired by works from preference learning, specifically from the comparison queries. We believe that this type of queries is simple enough for a user to answer without requiring high expertise, in contrast to other types of queries that are used in preference elicitation. Mainly, they pose two examples to the user, asking her to state her preference between the two. We have two types of partial preference queries in constraint acquisition. First, we have the case where both examples are partial assignments over the same subset of variables. Basically, this is very similar to comparison queries, but it also allows partial assignments and not only complete solutions of the problem. The second type of preference queries is in the case where one of the examples is the projection of the other in a subset of variables. This query basically asks the user, does the example with more assignments offer greater satisfaction of your preferences than the other? Or, is the additional information in this example satisfying some more of your preferences? We use both types of preference queries in different parts of our proposed algorithm in order to learn a soft constraint. Now let's focus on our proposed algorithm. Interactive constraint acquisition typically uses the following procedure in order to find the target network using version spaces. First, generate a query and post it to the user. Then, update the version space based on the answer of the user, either by learning some constraints or by excluding some candidate constraints, shrinking the version space. Then, if not converged, return to step 1. We will use this procedure too, but with several differences compared to the acquisition of hard constraints. Let's now focus exactly on these differences. First, when acquiring hard constraints, the system can learn a constraint only when it is violated by the example posted, as the violation of a constraint from the target network is what triggers a negative answer from the user, while the satisfaction of the candidate constraints does not really give any information. On the other hand, when acquiring soft constraints, the satisfaction of one or more soft constraints from the target network can trigger a specific preference from the user to one example over another. Another difference regards the information derived from the user answers to the posted queries. The answer to a membership query concerns all the variables that are instantiated in the example posted. Either there exists a violated constraint in this set of variables or not. In contrast, the answer to a partial preference query comparing an example with its projection in a subset of variables concerns the variables that are instantiated in one of the examples and not the other, if the additional assignments led to the satisfaction of a soft constraint of the target network. Finally, exactly because of the previous differences, the procedure we used when trying to find a soft constraint is bottom-up. trying to exploit the information we get from the answers to preference queries regarding the additional variable assignments in one example over the other one. While in constraint acquisition of hard constraints, the procedure is typically top-down, reducing the variables that are instantiated in an example in order to find the violated constraint. Here we can see the main idea of our method. We first decompose the example generated as much as possible by removing half of the variables from the example in each iteration. After we have decomposed the example as much as possible, we start searching in a bottom-up way, comparing the examples with each other. With this way, we ensure a logarithmic complexity in terms of number of queries posted to the user for the procedure searching the scopes of the constraints. This is our proposed algorithm for learning soft constraints, namely PREFAC, using the candidate elimination procedure as mentioned before. The main function of our algorithm is search_sc, which is the one updating the version space by learning the soft constraints and removing constraints from the candidates in the bias. It is a recursive function doing the decomposition of the generated example with recursive calls. Here we can see the main parts of this function. I will not focus on a lot of technical details in depth, but let's see the most important parts. First, we have the decomposition of the example as much as possible, as described before, and this is done with the recursive call at the beginning. Then we use a technique to ensure soundness, in case we already have found soft constraints in the variables that we currently search. Then we make sure they will not affect the answers of the user. We use a method similar to the one used in mquack algorithm for this, with the function findAllCons. We basically ensure that before searching in an example, it does not contain the entire scope of a constraint that is already learned. Finally, we post the example to the user when the decomposition is finished, and depending on the user's answer, the version space is updated. Importantly, if the user indicates that she prefers the example with the more assignments, then the algorithm does some more recursive calls in order to focus on searching on the set of variables that, based on the answer of the user, includes at least one variable of the scope of a soft constraint, satisfying more preferences of the problem that she has in mind. We can see this in this example. Assume the previous decomposition and assume that the user answered with a preference at some point. Then the algorithm tries to focus on that set of variables that led to the satisfaction of more constraint. Our method uses the same way as before to find the rest of the variables from the scope of the constraint we seek. Note that the variables that have been found do not include the scope of any satisfied soft constraints from previous queries from the previous decomposition, are included now in all the examples in the second decomposition, while only the other half of the variables is now decomposed, reducing the block in which we search for the constraint. After the scope has been found, findSc and findSc2 are used to find the relation of the constraint. FindSc is the main function used to find the specific constraint, while the second function is used only in cases where any constraint from the target network that was already learned is also satisfied in this set of variables that we search. In this case, the satisfaction of that constraint could affect the answers of the user in the preference queries, so different techniques have to be used in order to avoid that. The main idea of findSc is the following. Generate an example in the scope that we search that satisfies a subset of candidate constraints than the example given to findSc. Note that the example given is the one that we used in the previous function, but with assignments only in the scope found to contain a constraint that we seek. Then the function asks the user to compare the generated example with the given example and update the version space accordingly. This procedure is continued until the specific constraint has been found. If findsc cannot generate such an example because of the satisfaction of some constraints in subscopes that can potentially affect the answers of the user, then findsc2 is used, which uses two techniques to ensure that it will find a constraint. First, it tries to generate two examples satisfying the same set of learned constraints and a different set of candidate constraints, and follow the previous procedure again by comparing the two examples and update the version space. If it cannot generate two examples satisfying the same set of learned constraints, so they do not affect the answer of the user in which one she prefers, then findsc2 tries to generate one example and decompose it in order to compare it with its projection in a subset of variables satisfying the same set of learned soft constraint again. So the additional variables assignments can give us information about the constraint that we seek. Having presented our algorithm, let's now focus on our experimental evaluation. We considered only the learning of soft constraints of Max-CSPs, while the hard constraints, if exist, are assumed to be either known or acquired via another constraint acquisition system. As we use some randomness, for example in the value ordering heuristic, we run prefaq 5 times, and then we present the average and standard deviation. We use some heuristics that are shown to be efficient in normal constraint acquisition of hard constraints, with some modifications in order to fit the objective of satisfying the candidate constraints in the case of learning soft constraints. We used the exam timetabling, radio link frequency assignment, and some generated random problems as benchmarks for our evaluation. We focused on the evaluation of the number of queries and the time needed to converge. We also present some other important metrics, like the average waiting time for the user after a query is posted until the next one. The results in all benchmarks are promising. We can see that the number of queries is proportional to the number of constraints learned, while the time needed is acceptable in all instances. Especially, the average waiting time of the user between two queries is very low. Note that we evaluated our algorithm in the extreme scenario where no soft constraint is known and no soft constraint could be learned via a passive method by using some training examples we have from the problem. So the learned network is empty at the start, as no background knowledge has been used. This is the reason that the number of queries may seem high, but in real application background knowledge could be used one way or another. Concluding, we have extended the framework of active constraint acquisition to the learning of soft constraints in Max-CSPs. We introduced partial preference queries in the context of constraint acquisition and presented a novel algorithmic procedure. The results of the evaluation of our algorithm seem promising. We also have a proof of correctness for our algorithm that is not in the paper because of its length, but it will be included in an extended version of the paper. Thank you a lot for watching the presentation of our work.